All right, good morning, everyone. We are going to jump right into our energy panel. And I'm not going to spend a lot of time on introductions so that we can get to Q&A at the end. And I'm also going to reserve just a few minutes as the moderator to kind of cap the discussion after each panelist has an opportunity to present. But I will say, as a framing device, we all know that there's been after 80 years of business as usual in the energy sector, where there's lots of centralized generation, there's been a transformation of energy generation and consumption in cities. And the focus of that is a set of overlapping concentric circles, starting with the building, and then moving out to the neighborhood, moving out to the utility grid, moving out regionally to governmental policy and things like that. And the way that we are going to have our panelists present is starting with the smallest, most concentrated space, which is the building and the microenvironments around it. And then we'll scale out to the utility and then even broader out to a policy focus. And so Yoram has kindly suggested that we get right into the content. And so what I'd like to do is invite Evyatar Errell to be our first panelist and to present. He is an architect from Ben-Gurion University, but he also brings with us an awareness and tremendous expertise on how buildings affect the microclimates around them, how they affect the biosphere around them. So it won't be just a focus on the building, but the surrounding areas. And throughout today's discussions and presentations, the goal is going to be how has energy innovations in cities sort of occurred at different geographic scales. And I should also say, I didn't really introduce myself. I'm J.R. DeShazo. I'm the director of the UCLA Luskin Center for Innovation, and we work on a variety of sustainable energy, climate change, water, electric transportation issues. So it's really a pleasure to be with you all today. Dr. Errell, would you please come on over?
Good morning again. It's a pleasure to be here. I'd like to start my talk 40 years ago, and I'd like to start it right here, not far away. Ralph Knowles proposed a concept that he called the solar envelope and solar rights. And this was the 1970s. For those of you who remember the energy crisis following the 1973 war, a second energy crisis following the deposition of the Shah in Iran. And he suggested that the solar envelope is proposed as a zoning device to achieve solar access by regulating development within limits. And they're derived from the sun's position and the relative motion to the earth and so on. And this would thus offer the chance to replace unreliable energy resources, by that he meant conventional at the time, and to enhance the quality of urban life. So that's quite a big statement. What has happened in the ensuing 40-something years? Well, not much, because his concepts were right. Solar geometry hasn't changed, and we haven't really changed the way we build our buildings in many important ways. But there are a few examples that actually of neighborhoods that have incorporated what Ralph Knowles tried to do, and one of them is the place where I come from, in Sde in Israel. And an example of what a solar envelope would look like is, in this case, a very simplified representation of just a plane, which is a limiting factor which does not allow you, when you build a new house, to build higher than that limiting plane, so that you would not cast a shadow on your neighbor's house. And therefore, your neighbor could enjoy the benefits of solar electricity for passive heating, for heating water, and so on. So what the neighborhood actually looks like, and this is a model of a group of buildings, is something that has groups of 4 buildings, and within each of these 4 buildings, the buildings are pushed out to the 4 corners. So they're further away, they're spaced out, and therefore they're not casting a shadow on each other. Now, to the best of my knowledge, this is the only solar neighborhood in Israel which has plenty of sunlight. There are actually very few neighborhoods around the world which are constructed according to the same process. And here we are 40-something years later, and we need to look again at this concept, and that's what I'm going to try to do in the next few minutes. So if you look at the original solar houses, as they were called way back in the 1970s and 80s, the house on the left is Doug Balcom's house, and he was one of the pioneers of passive solar houses. And he built a house that was mostly focused on passive solar heating that's reducing heating costs in winter. It's in Tucson. And there wasn't much thinking about solar energy in terms of generating electricity. It was all about reducing consumption and passive heating. On the right, you see a building of the Bullitt Center, which is a high-tech office building in Seattle. Seattle doesn't have a lot of sunlight, and they have focused their interest in terms of energy on conservation, as you would expect, high insulation and so on, but also on electricity generation. And if you look at the building, the crowning achievement, if you like, is the crown on the top of the building, which is an immense solar PV array, which is only limited by the limits of the site itself. If they could have had access to more airspace above the street, they would have made it even bigger. So there's a there's a shift in the focus here. So why has it changed? Well, obviously because PV has become much cheaper. But that's not the only reason. Once electricity, which is distributed, became cheaper, you can distribute it over the grid in both directions. So suddenly the grid, rather than being a mono-centered radial arrangement where power is generated in one location and is distributed all over the place, you can generate electricity in different places, and it can move up and down the grid in both directions. Electricity is related to transport in a way that solar energy in the old fashion never was, because you can use it to power cars now. The information economy supports smart grid management, whereas your passive solar building was essentially an isolated benefit for the owners, for the occupants of that particular house. And decarbonizing the energy economy seems to be a more effective motivation for people to do this sort of building than simply saving a little bit of money in energy was in response to the crisis of the 1970s. The problem with that is that the utilities are absolutely scared, because this is a complete overhaul of their model. It is the ultimate disruptive technology as far as the energy utilities are concerned. Moving to solar energy, if you look at the traditional power station, can be done essentially in two ways. You can replace the traditional model with one of those centralized PV or concentrated thermal stations similar to what you have here. Or you could move to that model, which is in Freiburg in Germany, where every house has their own PV array. And these are two completely different concepts, because the bottom one signals a shift, which is probably the first shift away from the city as an organism which has or relies on an extended hinterland, and one that has been historically been growing in size as we go along, into one which theoretically is reducing the extent of the area the city relies on. Now, architects and people in the green building community have been focusing on this idea of a zero energy building, and it has certain permutation. It can be a zero energy building is one that is completely independent of the grid. It can be a zero net energy building, which means it generates as much electricity over the course of a year as it consumes, but that's not zero at all times. Or it can be a nearly zero energy building, which is a sort of a compromise. We'll try to reduce reliance on the grid as much as possible, but it's not a true zero energy building. Which would then lead me to ask, okay, why the building? Why is the building the unit of interest for architects and designers? Well, because historically it's always been that way, because it's easier to manage, because it's easier to build, it's easier to generate the infrastructure for. But if you look at the building, and I'll take as an example a residential building in Israel. A lot of buildings were built this way in the last 3-4 decades. Typically 3 stories high. It'll have 4 apartments per floor, 12 apartments, 3.5 persons per apartment. And when you get into that, you see that there is simply not enough sunlight, not enough electricity to provide electricity for that unit of measure. So what can we do? We can reduce consumption. We can increase the utilization factor of the PV. We can only live in single-family houses, or we can move to sunny locations. This leads me to the concept that a different scale might be a better way of doing it. If you look at solar rights, Israel, way back in 1970, mandated passive solar water heating. The trouble is it didn't mandate solar access. So what you have is this building has solar heaters on the roof, but it doesn't have sunlight. California has done the opposite. It has actually regulations for solar access, but it has no mandate. So if you look at what actually happens is that there's room maybe for us to meet with Californians to decide on how to do it more effectively. The solar rights issue has come up again in Israel now that we're starting to build high-rises. And when we build high-rises, they cast shadows, and they can cast some pretty big shadows. And this is a study for a 12-story complex of apartment buildings in a low-rise neighborhood. So it is a problem. PV output varies with location and panel orientation, and when you study that over the location of the US, you find that surprisingly, rooftop provides a substantial proportion, or can provide a substantial proportion of electricity in different locations, but not necessarily the ones you expect, because Arizona, New Mexico are nowhere near as much as New York, for example, or Maine, which has a lot of potential. Now, why is that? It's not just the sunlight, it's the density of the building, and it's also the way you construct your cities. So if you look at the equivalent number for Israel, it's 32%. Here in California, we're up to 50%. But sunny places like Arizona, right next door, are a lot less. And this is partly because people use electricity differently and to different amounts. And Americans use a lot of electricity. Israelis use about the same as the other European countries. So can PV be a big component of our electricity requirements? Yes, but we need to consume less electricity to begin with. Which leads me to this concept of a carrying capacity and urban density, because urban density is something that is related to in terms of transport and so on. And if you could borrow this concept from ecology of a carrying capacity, you come up with an idea that suggests that, yes, we only need about 2 or 3 or 5% of the total area of the city to generate enough photovoltaic electricity to provide all of our needs, even in a place like Pittsburgh, where I'm spending my sabbatical year now. But if you're US general, then the area becomes greater. So you can actually calculate how dense you can want your city to be, and 2,000, 4,000, 6,000, 8,000 people per square kilometer is really not a problem. You can generate enough electricity. Density can be achieved in different ways, and I want to focus just my last couple of slides on this idea of how you achieve density, because in the US, the solution is low rise, low density, mostly. And you can see here that essentially all of the buildings have sunlight because they're low rise, no one's casting a shadow on them. But if you look at Barcelona, and on the right, a typical high-rise development in Israel, the situation is different, because Barcelona has the old historical quarter is low, medium rise, medium or fairly high density. New buildings in Israel and just about anywhere else around the world are looking more like the one you see on the right there. And that building there is an image of a tower in the park, and is that what our cities are going to look like? They don't really look like that in Israel, and I'm sure they're not going to look like that anywhere else, but that is a big problem in terms of how we design our cities. So I'm, in the limits of time, going to skip the two elephants in the room, which are cost and the fact that solar energy doesn't really provide us energy all the time. And I'm going to go to my concluding slide, which is that. Industrial historians point out that new powers often become available long before the process that best use them are developed. And this I'm quoting from the Economist newspaper a few weeks ago. And when electric motors were first developed, they were deployed like the big hulking steam engines that came before them. And it took decades for manufacturers to realize that decentralized electric motors could do the job in a much better way. Which leads me to three concluding thoughts. If we want to actually have improved implementation of PV, we're going to think about the smart grid, we need to think about smart regulation, and we need to think about new social and economic arrangements to promote shared generation and storage. And I think all of these questions are the questions that should guide our discussion. And I hope that organizers make the presentations available so they can look at the cost data and the other information that I didn't have time to give everyone. So thank you.
Thank you, Professor Errell. That was perfect because we are going to focus on smart grids next, and then we will focus on cost and policy last. I do want to point out that very recently, the City of San Francisco adopted a requirement that all new buildings contain solar panels, and it was building off of a state law I'm sure no one knew about, that you had to set aside at least 15% of every rooftop space that was constructed to make it solar ready. So they're kind of taking it the next step. And of course, the question we're asking here in Los Angeles is, how are we going to beat San Francisco at that? So without further ado, I would like to invite my dear colleague, Rashid God, to the microphone. Rashid is an engineer, an expert on microgrids, and the challenge of solar intermittency, the challenge of connecting solar to electric transportation, and developing reliable, sustainable microgrids is Rajit's life mission. Rajit, welcome.
So I think that the first presentation was perfect and very timely, leading into the kind of work that we're doing, and it ended with the sort of the needs, and one of the needs is to modernize the electric grid. And so the question one is left wondering is, why do we need to modernize the electric grid? I think very simple. You know, if you looked at the mix of energy consumption here in Southern California, about even when I started in UCLA around 2002, the amount of solar, both central solar as well as rooftop solar, was very small. And GR can tell you the exact numbers. I'm an engineer. All I see is that when the amount of solar increases, we have greater amount of intermittency of the energy generation on the distribution side, on rooftops. Well, I'm an engineer. I look for a problem to solve. That was one of the problems I saw. The second problem I saw was electric vehicles were coming in. When we started this research in UCLA, there were no electric vehicles. I mean, there were like some golf carts here and there, and there were some very diehard fans who had the electric cars with the sort of the paddle inductor connector. And today we have almost close to roughly between 800 to 1,000 plug-in vehicles. I met the first Nissan Leaf driver on campus, and I installed the first EV charger on campus as part of my research project that I'm going to talk about. And today, I have 136 EV chargers installed on campus that are managed by our system. So we have two problems. Electric vehicles are plugged in the morning. There's a heavy load. Solar panels are coming in. There's a heavy load in the morning. Solar panels come in. They kick in later in the day. You have a little bit of a mismatch. Question is, how do you solve these things? And I argue that the growth of electric vehicles and the growth of solar will be correlated, because electric vehicles using the battery can be used as an energy storage device on the grid. There's a little video out there with a bunch of us colleagues here and President Obama, and I think I'd encourage you to look at it. It's part of the Grand Challenge program. But I'm going to talk a little bit about the electric grid. So this is the UCLA campus, and on the left-hand side, we have essentially on the left-hand side, we have the power grid, and then you have the UCLA campus. UCLA is a microgrid, and we rely on energy for internal energy consumption from the big grid as well as our cogeneration. So we mix the electrons from the big grid and our cogeneration to serve the rest of the campus. The traditional model of the grid has been central generation. That means the power flow is one way. The information flow is one way, and the control flow is one way, from left to right, from the big grid operator to us small folks who turn on the lights and the air conditioning and so on and so forth. Well, in the future, we're going to be installing solar panels on the rooftop. We're going to be having electric vehicles, and we are going to be able to generate our own energy, store it in the electric vehicles, and use it when we want to. And to me, that is incredibly empowering, and that's where I think a lot of the research that we're doing in the UCLA Smart Grid Research Center is falling in. And what does it mean? It means that in the future, the power flow, information flow, and control flow will be bidirectional. That means I will be able to purchase a solar panel and an electric car and plug it in, and somebody out there, whether it's a grid operator or an energy service provider, would be able to know that I have done this. It's like, it'll be like a cell phone. You turn on the cell phone, Verizon knows it's you. And you will start to automatically get a service. And so I argue that's going to be the model of the smart grid in the future. Electric cars. We have a lot of electric cars. How many of you have a plug-in or hybrid plug-in? Can you raise your hands? Okay. I'd like to see that number at 50%. Well, there you go. Yes. I can talk about a wireless electric vehicle charging project I have for self-driving cars as well at a future date. But let's talk about the real stuff today. These are electric vehicles parked in parking lot number 8, and the charging station on the wall was completely designed and built by our students. And when we started this research, there was not a lot of advanced technology. And so what was the idea? The idea was that if you had electric cars and you plugged it in the early days, we figured out that if everybody on campus gets an electric car, plug it in, the load will be more than what UCLA actually even generates with a cogen, which is around 40 to 50 megawatts. And so we realized that we have to be smart about EV charging. There's a lot of energy on the grid at night and in various times of the day, for example, when the sun shines in the afternoon. So why not use the fact that you can plug in your car for 8 hours a day, and then you essentially can do smart management using software. So we have mobile apps that every EV driver has, and using the mobile apps, we are able to, and that's a picture, for example, of our EV charger. And one of the cool things we did was we said, okay, one of the challenges is capacity. And so what we said was people need energy. Let's say at 5 p.m., you need to drive 40 miles. That requires about 14 kilowatt hours. That means on a 220 volt, I can charge you in 2 hours. That means on an 8-hour day, on one circuit, I can charge 4 cars. So that's what we did, and that was a very interesting research innovation that is in the process of now being commercialized by the students. So the point of it is that you want to be smart. You don't want to add a lot of physical infrastructure. You want to add virtual infrastructure. You want to manage energy. We need energy. We do not need power. We need energy. So if we can manage energy, we can utilize excess energy on the grid when the demand is low. This is another interesting research project. This is called vehicle to grid. And here what we're doing is we're taking energy from the grid when there's excess energy and giving it back to the grid. So for example, that student, on one particular day, you see the stator charge is green, but at the end of the day, the stator charge in his car is less. And he's able to still get home. So the point is, on some other days, the stator charge is sort of here in the morning. At the end of the day, it's higher. And so you can actually plan how much stator charge you need, and the system, the software will do it for you. So we built this prototype. It is now up and running. It's installed. It's functional in what is called the Los Angeles Department of Water and Power, a home of the future and garage of the future. This research has to do with energy storage. That's a battery energy storage system. This is now being installed in parking lot number 9 in the next few weeks. What does it do? It looks at the different problems on the grid, on the microgrid, and tries to solve them. And so what are the problems we're looking at? One of the problems is, I'm sorry, I think there's a little bit of a problem in the animation because the Windows Mac problem, but I can't get the animation. But I'm going to talk about the problem. The problem is this. This is a high-speed charger installed under Sunset Village, close by. And what that does is the load is very peaky. It does a 50 kilowatt load and it goes down. Well, the grid does not like peaky load. So what do? We put this battery in the garage and it can smoothen out the load. That means when the 50 kilowatt load kicks in, the battery in the garage will feed the battery in the car. And then when there's no load, then the battery in the garage will actually get charged. So you can use an energy storage device. So for example, Tesla, and Elon Musk has introduced something called a Tesla Powerwall. That can be used for homes. Our approach is for the microgrid. Again, these animations are not going to work, so I better just keep on moving forward here. This is another interesting problem. So what happens on the grid, on the microgrid, as you have more solar panels, you're going to have what is called variation in voltage and frequency, because the amount of energy available fluctuates as solar is intermittent, as talked about by the previous presenter. So we have this situation where you have variations in the voltage. So we can use a battery on the grid, whether the battery is stationary or the battery in the electric vehicle, to stabilize the voltage on the grid. So that's another technology that we have developed as part of the research. This project has to do with integration of solar panels, battery energy storage, and electric vehicles. and take all of the data into a master control center that we call the super control center. So this is in our lab. That's Dr. Peter Chu, one of our senior researchers. And he gets all the data. The key is that the software determines what to do. If there is, for example, today, let's say you have too much solar energy and you don't know what to do with it. Well, you could plan that do not charge your cars in the morning, charge the cars when the solar energy is going to kick in. Well, you do know that. You do have the daily projection, so you can utilize information about what's going to happen in the near future, and then you can plan for that day. So you can do very interesting sort of arbitrage, if you will, when you integrate solar, electric vehicles, and battery energy storage within the microgrid. This is also in Sunset Village. This is essentially a peak load situation with, we have 84 chargers installed, and you see this red is a peak load in the evening for fleet. Fleet vehicles come and return the cars around 3, 4 p.m. All of a sudden, you have a massive peak. Well, could you be smart about it? So what we do is that we optimize using this blue curve. And what is the blue curve? The blue curve essentially looks at every individual EV driver schedule, and it ensures that every driver will get the energy they want when they want it, if they come in at 5 a.m. or 6 a.m. or whatever it is, but yet minimize the cost of energy to the facilities operator using an optimization function. So this is an actually working system, and we've tested it out over the years. As I mentioned, we have a bunch of EV charging stations developed by us. We have installed 217 EV charging stations in the greater Los Angeles region. One is in the Department of Water and Power, one is in Southern California, Edison, and then we have a bunch of in the city of Pasadena, Santa Monica, so on and so forth. So I'm an engineer, so one of the things I do really well is I stick to schedule. I showed up 5 minutes before my talk, and I finished my presentation on time. JR, how's that?
That's awesome, Rajit. Thank you so much. And so we started out with the building and the site design and the challenges and the progress. Then we scaled it up to essentially, when we think about UCLA, it's a big neighborhood. It's a community. And the microgrid that is needed to manage the integration of these innovative generation technologies like rooftop solar and electric transportation. And Rajit did a wonderful job of outlining the challenges, the engineering challenges that have to be resolved. And I just want everybody to see, this might look like a little pilot here at UCLA, but these are the challenges that your substation that serves your home will face as distributed generation, solar panels go up in your neighborhoods, more people buy electric vehicles in your neighborhoods. We try and transfer power back from local sources to the grid and balance out the engineering requirements. So, these are technologies that are going to diffuse across communities as we innovate and as our cities become smarter. But none of that will happen if we don't have policies that incentivize the adoption of both electric vehicles and distributed generation. And so it's my delight to introduce our next panelist, who has been a tireless advocate for distributed generation here in the Los Angeles region and across the state of California. Mary Leslie, who's the executive director of the Los Angeles Business Council, and with whom I've had the pleasure of working for, I think it's 8 years now, on one of the more innovative solar procurement programs called a Feedin Tariff, which is very common in Europe, but not as common here. And she's going to help us understand the sort of the lay of the land and the challenges that we face as we try and adopt policies that will scale these innovative technologies, which are available to us, but we still need to adopt, and we need public support to do that. So Mary, welcome to the microphone.
Okay, thank you, JR, and I think that's a perfect prelude to my talk. Can you show me how to forward right here? Perfect, okay. So I think both Jacob and Rajit really laid the groundwork for what we're doing in the city, county, and state. JR, as he said, was our guiding star. Without him, we would not have a policy in the city of Los Angeles at the LADWP, because it was really incumbent when developing solar policies that we had to do the real work on the ground, connecting the dots. We had to actually design and price an actual feed-in tariff, as Mary knows, my friend Mary over there. And that required a top economist to help model that. Because as you can see from my first slide, we aspire to maximize the 19 gigawatts of solar roof potential we have in Los Angeles and Los Angeles County. And basically, we entered through a feed-in tariff, but I think our long-term goal is really to see local solar fully developed, because we think it brings great economic and environmental benefits to the city of LA that large-scale solar in the desert does not. So with that, I'm just going to spend 1 minute, assuming most of you in this room absolutely already know what this says. This is the regulatory and legal structure that's driving renewables in California, and thank goodness it's been a very consistent one in which our political leadership has stuck with, no matter what happened federally or what happened locally. So it was really a guiding star to why businesses even had an opportunity to step up what their role would be in it. And I think business in general doesn't really want to be the ones always opposing environmental regulation. You know, our organization has made a commitment for the last 15 years to work because we embrace the economic environmental sustainability as our goal. We don't see these as mutually exclusive things, that we can benefit by meeting the environmental regulations in our state. It becomes a competitive advantage to business to do so, and anything less than that is really a mistake. So with that, we can thank Governor Schwarzenegger, a Republican, for leading the way. We can thank a woman, Senator Pavley, for giving us AB 32, which really is governing us right now and is allowing us to require all of our utilities to get to 33% renewable by 2020. This has now been further realized by Senator De Leon's bill, which passed and was signed into law last year, which gives us a midterm goal of 50% renewable by 2030, and then, of course, the long-term goal that by 2050 we'll be at 80% renewable. These are really quite revolutionary goals. The fact that we're almost to 33% right now and it's 2016 is really astounding, and that's really happened with large and small scale renewable development, wind, solar, and other means. So what happened? What happened was that we have almost 3.2 gigawatts interconnected in California right now, which is really makes us leaders in the country. It also meant that we created a lot of new jobs. When our economy turned down in 2008 and we were a real estate-based economy, development-based economy, this was an area of growth, clean energy jobs. It also allowed us to take seriously that we needed to produce our own renewable energy business in Los Angeles, because I see several of my colleagues here from Lacey and other places, Mike Soares, yeah, he's waving, you know, they're really working hard to create the clean energy jobs and support them citywide. In addition to that, as my colleague just said, the reduction in solar costs really made the difference. I don't know how many models JR did of what we needed for the subsidy to be when it was in the middle 20s. The fact that we got it down to 13 cents makes us the lowest cost fit in the United States right now. In addition to that, when the federal government stepped up in December and extended the ITC tax credit for 5 more years, this really allowed people, you know, solar developers on the margin, business owners, to continue to embrace the program, knowing that they would have tax credit benefits. Okay, what happened here in LA? In LA, our bold, innovative mayor came right out of the gate talking about local solar. So this is a commitment to distributed generation in LA. Fortunately, the state government supported us in this with the net meter legislation in 2006, and then in 2009, the FIT legislation. We're actually mandated to do both. We're mandated to do 280 megawatts of net metered solar and an additional 75 megawatts of Feedin Tariff. So the state actually made a commitment to tell our utilities, listen, you got to do it, which was extremely helpful because as it was pointed out early, the utilities did not fully embrace this program. In addition to that, as you can see, not only has our mayor committed to 1,500 megawatts of local solar by 2025, but I consider much more important the 2017 goal, which is 400 megawatts of solar rooftop, plus 200 more under construction by the end of 2017. So we're really pushing hard on getting to that goal. Then the DWP has to be aligned with the policy goals of the mayor. It doesn't work. You know, under FERC law, they're responsible to FERC, a federal agency. So if their IRP does not reflect the policy goals of the mayor, we are not in very good shape. So fortunately, it does at the moment, or it's darn close. So we have been working diligently with helping them fulfill that mandate here at UCLA and at the LABC. In addition to that, we have some great other goals, 15% energy efficiency, which works complementary. We're not going to talk about that today, but it is contribute to our solar goals. Also, the DWP has 300 more megawatts of the feed-in tariff, which would take us to 450 megawatts by early 2020. As I said before, the net metered solar came into existence in 2006. It had a very slow ramp up, but it has been really exponential the last 2 or 3 years. So we're sitting at 168 megawatts of solar in this city right now, which is by far the largest in the country. We think there's an additional, 168 minus 280 of net metered solar, at least another 75 or 80 megawatts. We think there's this 110 megawatts of solar fit, plus an additional 40 megawatts, so that we would like to get very close to 150 megawatts here. I think the most important thing is our building and safety is now interconnecting NEM residential solar, which, as you know, rolls your meter back, and FIT allows you to generate power and sell it to the grid. That's the difference between the two programs within 2 weeks, which is outstandingly good. We would like the same for the feed-in tariff. Okay, so the feed-in tariff, as I said, was actually adopted by the LADWP board in 2013. It also had a very slow ramp up, but now is starting to really roll out. There's 2 kinds of feed-in tariff. There's a 100 megawatt FIT program that allows you to go up to 3 megawatts per project, and there's a 50 megawatt bundled FIT, which allows you to really go up to 20 megawatts. The largest project in the country will be a project that will interconnect at the end of this year or early next year at Westmont. It'll be 16.4 megawatts. So that's a big rooftop installation in a major city. It's one that we hope institutional players really embrace. We could really go very big on that, on warehouses, retail, commercial enterprises. We consider this quite an innovative program. To date, we have 14 megawatts interconnected of the FIT. We have about 60 in the pipeline. We have 35 in the bundled FIT that will all be realized, we feel. And the DWP has actually worked with us on some of the early megawatts that were really slow to coming online, to create additional incentives that they'll adopt in late June or July. As I said before, this is the least expensive feed-in tariff in the country. The economic benefits of the program, we spent a lot of time with UCLA developing, and USC. Basically, you create a lot of jobs, you get a lot of investment, you leverage federal tax credits, you reduce CO2 in basin. It's all good. This is really a pilot. JR worked with Manuel Pastor at USC. One of the goals of the program was to serve underserved communities. Solar had never had that as a goal. You can't have a program in the city of Los Angeles and not care about a very large group of people in the city. One of the complaints was underserved communities had no solar. Their legislators, their elected officials have been voting for this for years, but yet they had never received any of the benefits. This changed under the FIT. I'm very happy to say we have the first project in Boyle Heights they've ever had of solar. We have the largest project, and we have the largest program. But we want jobs to be targeted into the underserved areas, and we want the underserved areas to actually have solar. Manuel Pastor basically told us 40% of our projects are in underserved areas, so that's fantastic, and we want to keep that up. Key benefits to property owners, they have to be excited about this program. So I think we talked about all the reasons why they would be excited about this program. I'm going to show you a few of the models quickly. There's really 4 or 5 are very good examples of this program that benefit small business, manufacturers, retailers, multifamily, and warehouses. And I would suggest you go onto our website. You'll see all of these case studies on our website. I'm going to flip through them quickly. The largest right now is 5.1 megawatts at Forever 21. That's manufacturing. Oxnard Plaza was the first one interconnected in 2013. It was multifamily out in the valley. Southern California Trophy Store was a small business, been around 100 years. They bought their system and operate it. Boyle Heights was the very first project ever in Boyle Heights of solar on a roof, or solar of any kind, so this is important. And Westmont is the largest. So I would have you go to our website and take a look at that, because I want to get to the barriers real quick. Okay, and you can also take a look at these numbers JR ran on what 1,500 megawatts of local solar will get us by 2025, which is all good. Okay, next, barriers. Okay, the good news is that we have challenges, I guess. These are both grid and system reliability. As you know, the ISL put out the infamous duck curve. This issue of variability of solar is huge. Both things have to be addressed in order for the utilities to feel calm and in order for businesses to maximize the price of solar that they're paid. Aliso Canyon has now added another level of uncertainty because, of course, we get our natural gas there that makes renewable energy possible for the quick start powering. But we have a solution we really like. A bunch of new models are being developed, and two that we particularly like is one down at the Irvine Company with Advanced Micro Solutions Partnership with Southern California Edison, and the other with KB Homes. The one down at Irvine, you can see the benefits. Tesla batteries, 24 office buildings, reduces 25% of the demand, and creates a reserve for Edison. This is huge. If this works, 40% of all power is being consumed by commercial buildings. If this works, we have a solution. Thank you.